So welcome back. Just a reminder, as I put in chat, we have office hours immediately following this. So right after, I'll lecture until like 1:54, and then I will turn off the stream and turn it back on, and I'll put a link to office hours in on the announcement page on Elms. So anyway, so what were we doing last time? Last time I'd written out the definition of being orthogonal, which was two vectors have dot product 0, right? So that's the definition of orthogonal, and I'd written out the Pythagorean theorem in terms of the dot product or lengths of vectors. So if U and V were orthogonal, they satisfied the Pythagorean theorem. It didn't actually matter what space we were doing it in, so we can do it in Rn. That's perfectly fine. And so once we have the notion of orthogonality, so recall vectors U and V and Rn are orthogonal if and only if U dot V is 0. So remember, orthogonality is the notion of being perpendicular in higher dimensions. But you could also use if you use perpendicular as a term instead of orthogonal, it's perfectly fine. In fact, the shortcut name for what I'm about to define involves that. It's perp instead. So anyway, so I want to define an orthogonal complement of a space. So what do I mean by orthogonal complement? So this is the idea of an entire subspace worth of vectors being orthogonal to some vector or to some other subspace. So if a vector z in Rn is orthogonal to every vector in some subspace W of Rn, we say that Z, the vector, is orthogonal to W, which is a subspace. Okay. So this gives us a terminology now, not just describing, before our definition of orthogonal, it's only talking about two vectors, right? And I already told you that it doesn't make sense to say that a vector you have is orthogonal without then saying what it's orthogonal to, right? So orthogonal is only defined as it's a relative property. It's not something that a vector can have on its own. So similarly, that still is true for this new terminology. We say that a vector is orthogonal to a subspace if it's orthogonal to every single vector that belongs to that subspace. And so again, here this just gives us a way of saying that a vector is orthogonal to some subspace. Now that we have the notion of a vector being orthogonal to a subspace, we can consider the set of all vectors that are orthogonal to some given subspace. The set of all such vectors that are orthogonal to the subspace W is called the orthogonal complement of W. This is called the orthogonal complement of W and is written as W with this perpendicular symbol right here. Okay, this superscript that is a perpendicular symbol. And we read this as W perp, short for perpendicular. So this is what I meant by we actually still use the word perpendicular as shorthand of describing this orthogonal complement. So the orthogonal complement of W is written as W perp, and it's the set of all vectors that are orthogonal to W. So it's the set of all vectors that are orthogonal to every single vector in W. Okay. So what's some examples of this? Right? What's some examples of perp or orthogonal complements? So, for instance, say say I have a plane, right, in space. Let's say I have a plane through the origin in space. What is an example of what would be an orthogonal complement to that plane? Well, if I pick a line that passes through my plane that's perpendicular to it, well, if I make these line up so that, in terms of I don't have to shift anything. So let's just say that I have a plane through the origin, and I pick a line L also through the origin that's perpendicular to my plane. So my line passes through the origin. Why am I doing this? Because if I want to call these things subspaces, then they have to contain the zero of the ambient space, which is my origin, right? Otherwise, I would have to take my picture and move it around, which is fine, but let's just save myself the hassle. So if I have a plane through the origin, right? So here's space. Let's just, if this is x, this is y, this is z. Let's say that I take my xy plane as the plane in question. So I have plane through the origin. I'll just draw it like this. So I have plane through the origin. That's just the xy plane. This is my plane. I'll call it W. And then I take the z-axis, right, as a line that I'll call L. Oh, I'm a little bit off page. Okay. So L is perpendicular to W. Any vector in the subspace, in the subspace L is going to be some vector that lies along L. So if I think of the unit vector, it's going to be some scalar multiple of, of K here. If I'm thinking of my standard basis vector in R3. Any vector in L is going to be some scalar multiple of whatever vector I pick here. It's clearly going to be perpendicular to L. And of course, for this to be a subspace, set of all of those things is going to be L itself. And so L is W perp, or another way of thinking about it is L perp is W. Okay, that's another way of thinking about it. Oh, I used non-script L here, but I used script L here. Well, that's okay. I'll relabel this. No, oh, that's L. Okay. All right. So, what's going on here, right? This is the simplest example you can come up with something. I mean, you could do this in the plane as well, for two, like say linear subspaces in the plane. But of course, there's a lot of different examples you can come up with here. I'm going to mention two particular examples because this is a really, really nice way of kind of tying in some of these things that we first defined in chapter 4. So here's the following theorem that kind of lets you know that orthogonal complements is something nice. So maybe before I write this theorem, I'm going to tidy up first and say some facts. So facts, and then I'll state the theorem. So one, a vector. So a vector x is in W perp if and only if x is orthogonal to every x is orthogonal. Well, of course, if it's orthogonal to every vector in W, but actually I can say something a little bit more general here. So this is true if and only if x is orthogonal to every vector that's in a set that spans W, right? So x is orthogonal to every vector in a set that spans W. remember, W is a subspace of Rn here, so we don't have to worry about any infinite dimensional shenanigans. If W is a subspace of Rn, we know that it has dimension less than or equal to n, and so it has a basis. Since we're going to assume in this class that every vector space and every subspace has a basis, so it has some basis. So it's got some spanning set I can come up with, and so this is an if and only if statement that vector x is in W perp if and only if it's orthogonal to every vector in a set that spans W. So you have a spanning set for W. X is orthogonal to every single vector in that set. It's clearly orthogonal to any vector in W. You can prove that if you want. I'm not going to do it, but it's like a one-line proof once you recall that dot product satisfies everything it needs to dot linear combinations. Does every vector that is orthogonal to another vector in plane have an intersection point? Remember that we don't worry about intersections of vectors because you can consider every single vector as emanating from the origin. So all vectors intersect because the vectors are vectors emanating from the origin or they're points in Rn. So we don't care about where they actually sit in Rn. We can just consider all of them sitting at the origin. Gustavo, so the reason it couldn't be any other vertical line is because they wouldn't be through the origin. Yeah, I mean, it could. So it doesn't actually matter that the L is to the origin. That was just so that I could say that L is a subspace. But the picture would work just as well for any other vertical line L. I'm just toying around with me talking about sub. I want to consider it as a subspace. But of course I could translate that wherever I wanted to, and as a as a vector space, right? It would be the same thing. And same thing, yeah. You could choose any plane you wanted to, because what you're doing when you move something, when you translate a plane, when you translate a line, you're not changing anything really. The only thing you're changing is the origin. Okay, this is what's known as an affine transformation instead of a linear transformation. But there's basically what we're doing there is relabeling the zero. Yeah. But you don't have to get too philosophical with that. Basically, all this is saying is that if I'm drawing a picture like this and I want, I don't want to deal with any of this, I can just set everything at the origin instead. But it doesn't mean that that picture, if you take that picture and move it away from the origin, is everything still valid in terms of all the computations that were done? Yeah, it doesn't matter. Okay, so two. The second fact here is that W perp itself is a subspace of Rn. So this is what I was dancing around. So those last couple questions about does L need to be the z-axis in that example I did, this just makes it so that it's nice. You can say, oh yeah, clearly it contains 0 and all that. So yes, it is a subspace of Rn. If W is a subspace of Rn, then so is W perp. Why? Like, what's an easy thing to note here? So first of all, let's consider one. I said I wouldn't prove this, but let's go ahead and do. What direction do I want to do this? Let's do the backward direction. So let's say that W is equal to the span of some set. Remember, it has some basis. So let's say that W is equal to the span of some set. I'm going to use some letter or some vectors, W1 to WK. Of course, if W is a subspace of Rn, then some subset of Rn standard basis spans W. But I don't I don't have to do that if I don't want to. So anyway, so span of these vectors is W, we'll say, and we'll assume that X is orthogonal to every vector in this set. So X dot Wi is 0 for all I, right? So this is what we're assuming. And I want to show that then this is in W perp. So to show that a vector is in W perp means that it is perpendicular to any generic vector in W. So let W be in big W. Since we have a spanning set for big W, little w has to be written as a linear combination of these. So then this generic vector that's totally generic, it's just a vector in W, can be written as some linear combination, C1 W1 plus C2 W2, and so on all the way out to C K WK. All right, so here's my linear combination of W. Now let's dot X with W. Well, remember, we have all those rules of the dot product. It's very nice. I can pull scalars through the dot product, and a dot product of a sum is the sum of the dot products, right? It splits up across sums, behaves very well with respect to linear combinations. So what this is, if I actually go ahead and apply this, so I can break this up in the nicest way possible. So I'm not gonna go through step by step how that works. If you're confused, go back and look at the algebraic properties of the dot product. So this is C1 X dotted with W1 plus C2 X dotted with W2, and so on, all the way to C sub K X dotted with W sub K. All right, but X is orthogonal to each of these W sub i's, so all these are 0, right? So this is C1 times 0 plus C2 times 0, and so on. And so this is 0. And so we just showed that X is orthogonal to any generic W. All right, so X is in W perp. So we just showed the opposite direction. You can show the forward direction pretty easily. So I just showed the backward direction for 1. For 2, saying W perp is a subspace, what do I need? All I need is closure of vector sum and scalar multiplication, so long as the 0 in Rn is also in W perp. So question, is 0 in W perp? Well, remember, if I wrote this out in words rather than using this notation, this would be asking, is 0 orthogonal to every vector in W, right? Is the 0 vector orthogonal to every vector in W? Yes. Yes, it is. The 0 vector is orthogonal to every vector in any set ever, right? The 0 vector is orthogonal to every vector always, eternally. All right, and so the answer to that is yes. It didn't, this NW I could cover up. Is 0 orthogonal to every vector? Yes. Okay. All right. So 0 dot anything is 0, right? 0 dot any vector x is 0. No, it's not the 0 vector. It is 0 for all x in Rn. Right. So this is true for any vector. So 0. The 0 vector is orthogonal to everything. So it contains 0. Then a quick question. So that's the first thing we have to ask. Second thing, when we're asking about subspaces, is let's say that U and V are in W perp. Is U plus V in W perp? Well, if U and V are in W perp, that is, if U and V are perpendicular to every vector in W, is U plus V perpendicular to every vector in W? So let W be in W. Then let's dot U plus V with W. Well, this is U dotted with W plus V dotted with W. Again, those algebraic properties of the dot product. But what's U dotted with W? It's 0 because U is in W perp. V dotted with W is 0 because V is in W perp. So this is 0. So U plus V dotted with W is 0. W is just any generic vector in big W, so U plus V is in W perp. Similarly, if C is a scalar and U is in W perp, then CU is in W perp. You can prove that on your own if you want to. And so this is actually a subspace of Rn. That's all we have to check, right? Okay, so we have those nice facts. All right. Now, what I wanted to do is state this theorem, which nicely ties together some of this stuff. You can actually prove this with not too much work. It'll take you like two or three lines here. So let A be an m by n matrix. Okay. Then the orthogonal complement of the row space of A is the null space of A. Or sorry, it's the null space of it's the null space of A. And the orthogonal complement of the column space is the null space of A transpose. So then the orthogonal complement of the row space of A is the null space of A. And the orthogonal complement of the column space of A is the null space of A transpose. So written out in a much more convenient fashion, if I take the orthogonal complement of row A, this is the null space of A. And if I take the orthogonal complement of the column space of A, this is the null space of A transpose. And you can think about for a second why this is. It's actually not too complicated here. Remember what the definition of the null space is in the first place, right? Okay. So definition of the null space together with the row column rule for multiplying AX is all you need. Actually, that totally does it. Okay. All right, so now I want to define kind of the central concept going forward for the rest of this chapter, and that's the notion of an orthogonal set. Okay, so definition of an orthogonal set. So what's an orthogonal set? So it's an orthogonal set if so a set of vectors is orthogonal if they are pairwise orthogonal. Okay. Now you might say, wait, they can't fully be pairwise orthogonal because if you dot a vector with itself, that is never zero unless the vector itself is zero. That's true, and so they are almost entirely pairwise orthogonal. They're pairwise orthogonal except when you're dotting the vectors with themselves. So let's write this out. A set of vectors, say u1 to up in Rn is said to be orthogonal. That is orthogonal as a set of vectors. So they're an orthogonal set. So maybe I should say said to be an orthogonal set if each pair of distinct vectors is orthogonal. Of course, this is each pair of distinct vectors in the set. So i.e., another way of writing this is ui dotted with uj is equal to 0 for all I and j that aren't equal. Okay. So that seems like an innocuous enough definition. It doesn't seem like that's anything too crazy. It turns out this is an orthogonal set is extremely nice for a number of reasons that we're going to see. And it is so nice that we are going to frequently want to, if we have a set of vectors that we want to deal with, we are going to want to come up with an orthogonal set that does the same thing if the set of vectors is not already orthogonal. That process is going to be, we're going to have a special name for that, and that's going to be that's basically going to be the main computational thing we do in this chapter. So this chapter is, a huge chunk of this chapter is devoted specifically to, if we don't already have an orthogonal set, coming up with one. Okay, which we'll have an entire process together with it. So let's do an example real quick. So here's an example. So let say u1 be the vector 3, 1, 1. Let u2 be the vector -1, 2, 1, and let u3 be the vector -1/2, -2, 7/2. Okay. So I want to show that these three vectors constitute an orthogonal set. So I want to show that the set consisting of these three vectors is an orthogonal set. Well, how would I do that? Just by the definition, a set of given vectors is orthogonal if I look at the pairwise dot product of these things. If this pairwise dot product is 0 for all the distinct vectors, then I'm good. All the distinct pairings, then I'm good. So I only have three vectors here, so I would need to compute u1 dotted with u2, u1 dotted with u3, and then u2 dotted with u3, and that's it. All right, so three things I have to compute. So this is really easy to check. I just have to compute three dot products. So u1 dotted with u2 is what? So let's dot these first two vectors. So this is 3 times -1 plus 1 times 2 plus 1 times 1. So -3 plus 2 plus 1. So it's -3 plus 3. This is 0. Okay, so that's looking good. Of course, if at any point here I compute one of these and I get something that's not 0, and assuming I did everything correctly, that means the set wouldn't be orthogonal, right? So let's do u1 dotted with u3. Okay, so u1 dotted with u3, this would be 3 times -1/2 plus 1 times -2 plus 1 times 7/2. Okay. All right, so this is -3/2, 7/2, and -2. So that's -3/2, -2, which is -4/2, plus 7/2. So that's -7/2 plus 7/2, that's 0. Okay. And then one more we have to check. So that's u2 dotted with u3. So this would be -1 times -1/2 plus 2 times -2 plus 1 times 7/2. And you'll see that that is also, so here's 1/2 -4. So it's -3/2 plus 7/2. So that's 0, yeah. So this is indeed an orthogonal set, right? Those are the only three things we had to check. Okay. Okay, so I had a question. Is an orthogonal subset of Rn just n orthogonal lines to the origin? Not even lines, just vectors, I guess. This is one example of an orthogonal set. So for instance, you already have the nicest possible example of an orthogonal set, which is exactly the one that was just mentioned in the chat here, which was just take the standard basis vectors in Rn. Right, standard basis vectors, those are orthogonal. Now, can I arrange, you know, an orthogonal set that doesn't look exactly like those? Yeah, of course, right? I can just take that frame, right? So imagine that as a frame. Take that frame and just like rotate it, right? So now this is something that, of course, I think the original question was, is that in orthogonal lines? Those would still be, you know, that rotation I did would still be orthogonal lines through the origin, so that would still be the case. But you know, but anyway, the point is that an orthogonal set is a generalized form of the standard basis vectors in some way. And we get all of the nice things that are true for the standard basis in Rn for orthogonal sets. And it's exactly because of that fact that you noticed. Yeah, so then Gustavo asked, can you make an orthogonal set of eigenvectors? Yeah, so if you have say an eigenvector basis of some space, some Rn or some subspace, can you make an orthogonal set of that? Yes, you can. So we will have a process for this. This is called the Gram-Schmidt method, and we'll do that in 6.4. But anyway, so this is an example, and one thing I want you to note is that this was really, really easy to check, right? So if I gave you a set of vectors, I mean, okay, maybe if I gave you like a long list of vectors instead and asked you to show that they're orthogonal, so if I gave you like a long list of vectors in R7 or something and asked you to show if they're orthogonal, then you'd have to check a lot of dot products. But in terms of like conceptually, it's really, really easy to check. You're just computing dot products. And so, you know, if there's not too many vectors, there's not too many dot products you have to compute. So it's really easy to check if a given set of vectors are orthogonal. But the question is, how do you come up with one? Right? What about coming up with one? So imagine trying to do this, right? You start out with maybe you start out with one vector, then you kind of eyeball it and look for a second vector that's orthogonal to it, right? But then when you get to that third vector, you have to come up with a vector that's not just orthogonal to the second one you came up with, but also orthogonal to the first one, right? And if you try to do that a couple of times, you'll convince yourself that it's tricky. You can't this is not something you can just eyeball typically. It's actually something kind of annoying to deal with. And of course, the more vectors there are, the more annoying, right? If I gave you 4 vectors in R4, or if I wanted you to come up with an orthogonal set of 4 vectors in R4, you start out with one vector, right? If you're trying to build it from scratch, we'll say. You start with one vector, and then you're like, okay, you know, I can come up with a vector that's orthogonal to this, but then when you come up with that third vector, it needs to be orthogonal to the first 2, and then the fourth vector would need to be orthogonal to the first 3, right? And this quickly, when you try to do this algebraically, you're going to run into issues, okay? And so you'll quickly convince yourself that while this is easy to check, coming up with one in the first place is actually harder. It's more involved. And so anyway, there's a theorem that you might have noticed from looking at that example, that those vectors weren't allowed. Once we saw that they're an orthogonal set, they're actually not allowed to just be any old set of vectors. It turns out that if we have a set S of vectors, we'll say U1 to U sub P. So if this set is an orthogonal set, so this is an orthogonal set of non-zero vectors in Rn. Okay, then S is linearly independent. Okay, and thus is a basis for the subspace spanned by it. Is a basis for the subspace spanned by S. So for the subspace of Rn spanned by S. So this should really convince you of the importance of an orthogonal set, because being an orthogonal set is stronger than linear independence. Okay. What do I mean by stronger? I mean, if you have a set of linearly independent vectors, you already know how nice that is. But a set of linearly independent vectors is definitely not guaranteed to be orthogonal, right? If you just pick a generic set of linearly independent vectors, no hope you have for that being linear or for that being orthogonal. But an orthogonal set is automatically linearly independent. So being orthogonal is a much stronger condition than being linearly independent, and you already know that being linearly independent is a very nice thing. Yeah. So, well, now, Gustavo, that you've seen this fact, now you know the answer to the question of will the max number of vectors in linearly independent orthogonal set be equal to n? Well, now linearly independent orthogonal set, you don't have to say that. It's redundant. It's just orthogonal set, right? Because an orthogonal set is automatically linearly independent. Okay. And so. How does this go? Well, I don't have to do I'm not going to do the proof of this, but if you wanted to see, how this works, basically, what this means is that, if you have, any non-trivial linear combination of this thing, you could actually, say dot the entire thing with U1. Right, which automatically gives you everything you want, and you can do the exact same thing with all of the. Well, okay, I think that actually this is an important enough concept that I should go ahead and do this. So suppose that we have a non-trivial linear combination, or I don't even have to say that. I don't have to do this by contradiction. I can just do this directly. So suppose that I have a linear combination of these vectors that sums to the zero vector. Right. Okay, so suppose I'm in this case. Dot both sides of this with U1. All right, so dot both sides with U1. So U1 dotted with this left-hand side is equal to U1 dotted with 0. Okay, so what does this mean? So if I dot U1 with these things, so this, of course, has a distributive property, and I can pull constants out of it. So this is C1 times U1 dotted with itself, okay, plus U1 dotted with U2. I'm going to write that term, and then I'm not going to write any of the others, plus all the way to CP times U1 dotted with UP. And this is equal to the zero vector. And so, or sorry, not the zero vector, this is equal to 0, right? Because I dotted this, so this is 0 here. Okay, and so all of these are 0. Why are they 0? Because this is an orthogonal set. So U1 dotted with any vector in the set that is not U1, so U1 dotted with U2, U3, U4, all the way to UP, all those are 0. So all these get zeroed out, and so what I have here is C1 times U1 dotted with itself is equal to 0. Now, U1 dotted with itself is always non-zero so long as U1 is non-zero. This is an orthogonal set of non-zero vectors. So U1 is not 0, so this thing is not 0. So I have 0, or I have something times the thing that's definitely not 0 is equal to 0. This means that C1 is equal to 0. Okay, but I could have dotted this initial thing with any UI, right? I could have dotted it with U1, U2, U3, U4, whatever. I dotted it with U1, got that C1 was equal to 0. So by the same reasoning, by the same logic, C2, C3, C4, and so on, CP are all 0. So anytime you have a linear combination of these u's that's equal to the 0 vector, all the weights have to be 0. What does that mean? It means they're linearly independent, right? So that's it. You're done. Okay. Yeah, well, yeah, so someone pointed out in chat, I can't help myself. I see the thing, and then I convince myself that it's useful for you to, see how it works. So yeah, I have a hard time. Sometimes I can help myself. If the proof is longer than like 3 or 4 lines, then I won't do it usually. But anyway, so what you were saying then about orthogonal linearly independent set, well, orthogonal set guarantees linear independence. And so if you have a set of vectors that is orthogonal, and it's also the number of vectors in the set's equal to the dimension of the space that you're in, or either talking about the subspace or talking about the Rn itself, then that is an orthogonal basis, right? And so it makes sense to give a special name for that. So an orthogonal basis is exactly what it sounds like. It's a basis for a space that is consists of orthogonal vectors. So it's a basis that's also an orthogonal set. So an orthogonal basis for W is a basis for W that is also an orthogonal set. Now, W is just some subspace of Rn here. Okay. All right. So this next theorem that I'm going to write out is extremely important, but it doesn't have a name. It's just called like Theorem 5 in the textbook or something like that. So it doesn't have a name, but I'm going to refer to this so much. Maybe I'll just call it the nameless theorem because I will refer to it like a ton, but then you can think about whether or not the nameless theorem is nameless since I'm calling it the nameless theorem. So theorem, we'll call it nameless theorem, which now it has a name. So I'll let you worry about that. So the nameless theorem is the thing that tells you basically how nice an orthogonal basis is. Okay, and it is, I would say this is the primary motivation for having an orthogonal basis. So this is actually going to be the primary motivation for why we're doing all of the computations that we're going to be doing in Chapter 6. So this is extremely important. So let say U1 to UP be an orthogonal basis for a subspace W. So let U1 to UP be an orthogonal basis for a subspace W of Rn. Okay. For each vector y in W, the weights in the linear combination that is y written as a linear combination of these u sub I orthogonal basis vectors can be computed directly. So are given by if you want to compute a C sub j weight here, what is this? This is actually just y dotted with u sub j divided by u sub j dotted with itself. Now, many of you are going to see this and remember that this is, you have seen this before, right? And the hint is you've seen this in Calc 3. Some instructors at UMD don't talk about it that much in Calc 3 because it is something that is talked about an insane amount in this course and in other courses. But you have seen this before, or you have seen something very, very similar to this. I mean, you have actually seen this before in some capacity. But what is this saying? So before I go over this again, this says, so this theorem says that when a vector is written as a linear combination, so as a lincom of an orthogonal basis, so of an orthogonal basis, the weights can be computed directly. Well, what's the alternative? Well, the alternative is you would have to solve some, like a simultaneous system of equations, right, to find these weights. But this just says you can just compute them immediately using dot products, right? Okay, so I can find all those weights immediately. Now, as someone pointed out in the chat, yes, this is the scalar that shows up when you project a vector onto another vector. Okay, so in Calc 3, you mentioned the notion of projecting a vector onto another vector. When you project a vector onto another vector, well, then the vectors are necessarily going to be parallel. If vectors are parallel, they line up, with one of them is a scalar multiple of the other. The scalar in question is this. Right? So this is the scalar that you compute when you do projection this way. Now that's not a coincidence. In fact, it's the opposite. That projection formula comes from this. Okay. And in that case, the orthogonal basis in question is the standard basis. So in R2, when you're projecting a vector onto another vector, or in R3, when you're projecting a vector onto another vector, the orthogonal basis that you're using to use this theorem, so you're using this theorem when you do that, and when you do that, the orthogonal basis you're using is the standard basis of R2 or R3. Okay, so that's exactly what it is that's going on here. We're about to see why this is tied up with that notion of projection. First of all, how do I prove this? So this proof I'm actually not going to do because I can explain it in literally one line, just like we did in the previous proof where I showed you how that argument works. Okay, I have y here, right? What do? Dot y with, if you want to find c sub j, dot this linear combination y with u sub j. Right? So I have y dotted with u sub j. On the right, all these terms zero out except c sub j times c sub j times u sub j dotted with itself. Well, u sub j dotted with itself is some non-zero number. So I divide by it. That's it. Right? That's it. Okay, so this is immediate. Once you know the trick that I showed you in the last theorem, okay, or in the proof of the last theorem. So, for instance, as an example of how to compute with this, let S be the set of vectors u1, u2, u3. Let's reuse the same vectors that I used before. So just to remind you, u1 and u2, and u3 are these three vectors. Okay, so there they are. So I want to reuse those vectors. So reusing those vectors, so let S be u1, u2, and u3. So this is an orthogonal basis for R3. Now we know. There's three of them. They're orthogonal because we proved that in our first example. So they're linearly independent. So I have three linearly independent vectors in R3, automatically a basis. So this is an orthogonal basis for R3. Okay, so let y be the vector, say, 6, 1, minus 8. Okay. Express y as a linear combination of the vectors in S. Now normally what would you have to do this, right? If you're asked to express a given vector as a linear combination, you would have to solve a matrix equation, right? It would be really annoying. Here you can do like a few dot products and you're done, right? And computing dot products is really easy. So let's do this. All we have to do is compute like 6 dot products. So we do y dotted with u1. Again, let's remind ourselves here of the vectors. So there, I'll put them there. So y dotted with u1, so I have 6 times 3 plus 1 times 1 plus 1 times minus 8. So I have 18 plus 1 minus 8. So that's 11. And then I dot u1 with itself. What do I get? So I get 3 squared plus 1 squared plus 1 squared. That's also 11. Hey, nice. Okay, let's do y dotted with u2. So 6 times minus 1 plus 2 times 1 plus 1 times minus 8. So that is minus 12. So let's see, minus 6 plus 2 minus 8. Yeah, that's minus 12. And then u2 dotted with itself is going to be minus 1 squared plus 2 squared plus 1 squared. So that's 6. And then lastly, y dotted with u3 is going to be 6 times minus 1/2 plus 1 times minus 2 plus minus 8 times 7/2, which is, let's see, minus 3 minus 2 and minus 56 over 2. That's minus 6. It's minus 33, right? Yeah. All right, and then u3 dotted with itself is going to be minus 1/2 squared, minus 2 squared, 7/2 squared. So 1/4 plus 4 plus 49 over 4. So 50 over 4 plus 4 is, oh, okay, so it's 33 over 2. It's 66 over 4. Yeah, 33 halves. Okay, so so here's my computation of these 6 dot products. Now, by that theorem, I know immediately what my weights are. So thus, y is equal to C1 U1 plus C2 U2 plus C3 U3, where the C1 is y dotted with U1 divided by U1 dotted with itself, so that's 1. So this is U1. C2 is minus 2. And C3 is minus 33 divided by 33 over 1/2, so that's minus 2 as well. So there's y written as a linear combination of those u's. Okay. All right. The most important thing intuitively is that this just says that whenever I have an orthogonal basis, any linear combination, right, involving vectors in that basis, I can immediately compute the weights. I don't need to go through this whole process of setting up a matrix equation or anything like that. I can just immediately compute the weights. So this, look how much easier. Look, you did, like, all of this computation was done in, like, no space whatsoever. This was way easier than setting up some matrix equation and trying to solve that, right? So this is the key. Okay. So that's all I wanted. That's all I have time for today. So we'll finish this up. We'll actually, I should start on Gram-Schmidt maybe next time. Definitely by next Monday I will have finished the Gram-Schmidt process, which basically means that I will have finished Chapter 6 almost entirely. I'll have like one more thing to do next Wednesday, which is least squares. And after that, we'll be done with Chapter 6. And so after that, we'll be moving on to Chapter 7. So this, your next exam is going to be, I'll give it to you, I think next Friday. And it'll be due, the following week. So anyway, I'll remind you all in an announcement about that. It'll be identical in format to the last exam. Anyway, so it is time to restart now and have office hours. So if you have questions about the homework or any other questions about stuff we've done, you can hang around. I'll post the link in the announcements on Elms, so you can have a look out for that, and you can join and ask any questions that you want. And so I will be here for roughly an hour. So just let me know. Otherwise, I will see you all on Friday.